Okay, so welcome everyone to the two last lectures for this semester. So I really hope that as time goes on, you will slowly start appreciating the beauty of this field. I know that a lot of you are completely held down by your performance in assignments and exams and all of that stuff. Very soon you will find out that these things make really very little sense. The exams are 1 hour exams. They mean nothing with regards to whether you really understand the material or not, and it is going to turn out that maybe a semester later, when the shock is gone, maybe 2 semesters later, you will start finding what you have done here to be of interest. And if that happens, my job will be completely done. If it turns out that at some later point in time you open up a particular paper, just asking yourself, how is it that this person actually managed to do this problem? I thought this problem was hard. If that ever happens to you, remember me. I'll be telling you, thank you. This is all I was hoping for, basically. Okay. That said, let's come back to where we are right now. I've been told by the TAs that all your assignments and both midterms have already been graded and the grades have been put up, which essentially means that you need to now go and check your spreadsheet, your grades, and make sure that you have the numbers right. You don't want come Monday to suddenly realize that you were supposed to have gotten a 40 someplace and you have only a 20. Okay? Take care of those things right now. There are just 2 things left that will be part of how you get graded. One is the survey paper itself. It is going to get graded. I'm going to look at it to make sure that people haven't just copied from places, and you have your head sitting right, because writing papers is a very important skill to have whether you are doing a master's or a PhD. And then of course the final exam. And about the final exam, it's a 2-hour exam. I believe it is from 3 to 5 on Monday. Don't hold me to this, but please go and check the registrar's website. To the extent that I remember, it's 3 to 5 on Monday, and you are allowed 2 cheat sheets this time. Okay. You have always known that cheat sheets are of very little use. The questions are going to be very similar to what has been the case before. I just, as I told you, allow cheat sheets so that you don't have to be lugging around an extremely heavy book with you. And if there is any formula that you want to look up, you should be able to look up. It's your Google for that 2-hour period. So where are we? What I showed you last time was definitions of things such as the complexity class P. Then we did the complexity class NP. So this one, the difference between the complexity class P and the complexity class NP is that whereas both of them are decision problems, one can be solved in polynomial time, the other one can be verified in polynomial time. We then moved on to problems called NP hard problems. And NP hard problems are those problems that any problem in NP can be reduced to in polynomial time. So given any problem here, any problem in NP can be reduced in polynomial time. And this tremendous fact was essentially Cook's theorem, which I did not prove yet. Okay. What I basically did was said, let's just assume that this is the case, and Cook's theorem is essentially about the Boolean circuit satisfiability problem. I said, just assume for the moment that Cook's theorem is right, and I will show you that there are going to then turn out to be other NP complete problems. So an NP complete problem is a problem that is both NP hard and is NP. Okay, so in order to show that some problem is NP complete, we have to prove that it is in NP, which is usually the easier thing to do, and then you prove that it is NP hard, okay, which is the more difficult thing to do. And what we basically did was, assuming that the Boolean circuit satisfiability problem is NP complete, we then showed through the following polynomial time reduction that 3 CNF SAT is NP complete. How did we do that? Well, it is very easy to show that 3 CNF SAT is in NP. It's a decision problem, and the certificate we look for is the assignments to the various variables in there. You just stick it in there, you can verify. That was one piece. The second piece was the relatively more difficult piece, which was just going for this reduction, which essentially said that you give me any Boolean circuit satisfiability problem, and I will build you a 3 CNF SAT which is equivalent to it. In other words, I can see this problem through the eyes of this problem. This is what reduction is all about. Okay. I then made a rather surprising jump, and this I believe is a contribution of the other person. Richard Cart was working along at approximately the same time that Cook was working on these problems, and Cart produced a bunch of reductions to show that this is not the only guy out there. So there are a bunch of equivalent problems that seem to be all NP complete, and you can choose any one of those. And the one we did was K-clique. And the way we went around doing this is we said here is a reduction. If I can show this piece, of course, proving first of all that the K-clique problem itself is in NP. If I can do this reduction, it basically means that I can take any NP problem in NP, then with the first jump go to BCS, with another jump go to 3 CNF, then another jump go to K-clique. So any problem in NP can be reduced to the K-clique problem. Okay, and this is always the way we go around doing this. Mind you that whereas all of these can be reduced to K-clique, right? K-clique can be reduced to other NP hard problems in there. So for example, if you were asked this BCS, this it turns out is naturally the result of Cook's theorem, because Cook's theorem basically says any problem out there is reducible to BCS. So we have not only BCS is reducible to K-clique, K-clique is reducible to BCS, so they are of equal difficulty. So these are all problems, these NP complete problems are problems of equal difficulty sitting within NP, which are more difficult than some problems in NP, or that is what we believe, because we have not been able to prove that these problems do not have polynomial time solutions. All we have done is show that we have spent 40 years and we have not found any polynomial time solutions, and we can see that these problems are all related to each other, and the fact that you give me a polynomial time solution to any one of them, I will find you a polynomial time solution to all these people up there. Okay. So this is where we stopped last time. Any questions? Okay. So let me do the following first. Before going and proving to you Cook's theorem, let me show you a problem which I believe is of the kind of difficulty that you can expect in the final exam. And I'll try to speak out as I go about the problem so that you can see exactly how it is that somebody actually goes about solving these problems. So what I'll show you is the following. Okay, before I start, I want you to realize that we were in the domain of CNF, and then through this very beautiful reduction, we suddenly moved to the domain of graphs. Okay, so the K-clique problem is a problem in the domain of graphs. Once you have proved that there is a problem in the domain of graphs that is NP complete, you can start wondering whether there are other problems in the domain of graphs which are also NP complete. Okay, and here is one that you might expect to find in the exam. So if you're asked, prove that vertex cover is NP complete, you first of all have to ask yourself, what is vertex cover? Okay, so the concept of a vertex cover is very simple. So you're given a graph G, and you're asked whether it has a vertex cover of size k. So once again, what is a vertex cover? Well, a vertex cover is a bunch of k nodes such that every edge is incident on one of these nodes. In other words, these are nodes that are sort of covering all the edges in the graph. Think about it for a moment. There are a bunch of edges in the graph, and I am saying, can you cover all of these edges using k nodes, and by which we mean essentially what you mean by cover. So, if there is an edge out there and you have not chosen either this node or that node, then you have not covered this edge. Okay, there are a bunch of edges. Some edges are incident on one of your nodes, some edges are incident on both your nodes or two nodes in the set that you have chosen. You are not allowed to have edges that are sitting outside of the set that you have chosen. If the edge is sitting outside, neither side is among the nodes that you have chosen, then you have not covered that edge. Okay, it is a very simple notion of cover. It is the English notion of cover. So, the question is, given a graph G and a number k, can you find or is there a vertex cover of size k? Okay, good. So, let me make sure that you do not run into the standard problems that people run into, which is one, some people try to start solving this problem in their head. You have been asked to show that vertex cover is NP complete. I have not asked you give me a polynomial time solution to vertex cover. So, do not start thinking how it is that you will go about this graph picking up k nodes in order to get yourself a vertex cover. That is not what is being asked. Okay. So, set that thought out, and first of all, the easiest thing to get yourself the 0.5 points out of 20 is to show that it is in NP. Please do not miss that, you will lose points. Okay. This is part of your training. Okay. First thing to do is prove that vertex cover is in NP. Is vertex cover a decision problem? Of course, yes, the way it has been described, it is a decision problem. The answer is a yes or a no. The more important part is, can it be verified in polynomial time, and what would be your certificate? So, you are given the vertex cover problem, what would be the certificate? This set of vertices that form the cover. Okay? Very simple in this particular case, and then you have to say that it is very easy to show that in polynomial time you can verify it. Essentially, you will go through every edge and you will check and see whether one of the two vertices that edge is incident on is in your set, and if you can scan all edges, you are done. If they are always there in this set, you say yes. You count the number of nodes here. If it is less than k, you say yes, otherwise you say no. So, that takes care of the fact that the vertex cover problem is in NP. Now, is the problem of showing that it is NP hard. Here is a place where people again get confused which way should our reduction go. So, always remind yourself of the picture. So, here is all of NP, and you will choose some problem out there which you know is NP complete. Okay. You will be allowed that. Either I will say choose any problem, or I will say, I will give you a hint and say choose this particular problem. Okay. If that problem has been chosen, what has been shown is this. That is the problem that has been given to you. Your job is to show that the vertex cover problem is NP hard, and the way you go about doing that is do that. So, if you draw this picture out, you immediately know which way your reduction has to go. So, you are going to show this. So, I am going to choose this problem, and since we only know of one graph theoretic problem right now that is NP complete, we can try to make this transformation. Okay. So, you have set the stage for yourself. If I give you choose k click, in this particular case you do not know of any other graph theoretic problems which are NP complete. So, this is the first one. It is probably the easiest to make this jump. Okay. So, if you assume that 3 sat is NP complete, it is likely that that jump is going to be very difficult. So, always choose a problem which is pretty much in the same domain, and your transformation will be easier, your reduction will be easier. So, here is the problem then. The clique problem will have its own graph and the number k, and the question being asked out there is there a k clique in there. What I want to do is create a new graph and a new k, and this will be in the vertex cover problem, and I want to make sure that if this has a clique of size k, this will have a vertex cover of size k tilde. And if this does not have a clique of size k, this will not have a cover of size k tilde. Okay. This sounds very algebraic to you. But what you need to do is to understand what this polynomial time reduction is about, you want to see the clique problem through the eyes of the vertex cover problem. I will give you a clique problem. What can you do to it? That is all that is being asked to you. I will give you a clique problem. I will give you a graph. I will give you a number k. You are taking that and you want to do something to it. Something to it and hand it to your friend, and your friend seems to be good at solving the vertex cover problem. Assume that your friend can give you an answer. Your job is to take this clique problem, do something to the graph, give it to your friend who will solve the vertex cover problem in whatever time it takes. It is not going to take polynomial time, but whatever be the answer out there, you need to be able to presuppose that, if that is the answer, this is the answer. That is what you are looking for. You are looking for setting up the answers to be in such nature that as soon as you find the answer out there, you can say, this is the answer out here. Are you following me? Okay, some of you might find this very easy, but some of you will be having difficulty. So, stated formally, all that is said is that given a graph G and a number k, you are supposed to produce a new graph G tilde and a new number k tilde such that an answer yes is an answer yes is an answer yes. But that does not tell you exactly what you should be thinking about. What you should be thinking about is either, some of you like this, that can I see this problem from the eyes of vertex cover. The other one, which is much simpler, is to say, given a graph and a number k, if there is a clique, what can I do to this graph? Assume that there is a clique out there. What can I do to this graph such that when you look for a vertex cover of size k tilde, whatever you find will tell me where the clique is. And if you cannot find it, there will not be any clique here. Is that making sense? Okay, so here's what I'm thinking, right? I am going to assume, first of all, that the graph G has a clique. Understand that none of this is part of the theory itself. You cannot go and say that, let's assume that graph G has a clique. That's not what I'm saying. I'm thinking in my own head that I will get two kinds of problems, some with graphs of size with a k clique and some with none. And my job is not to solve for it. I'm just going to essentially run a transformation so that if you have a k clique there, this is where you will find the vertex cover. So this is what I'm doing. I see the graph G, and originally I'm going to assume that, hey, it's going to have a k clique, say. If it has a k clique, I am thinking that the way I want to create the vertex cover is to somehow, so here I am guaranteed that all these edges are between these nodes. Right? So somehow I'm saying a cover where every node is attached to at least one edge out there, and this one seems particularly different, where these edges are connected by both nodes. So the only way I can think of doing something is that I will go with the complement of this. Okay, so I'm taking the graph, I'm going to complement the graph. Can you sort of see why it is that I'm thinking about complement? See, on this side I'm saying that all of these edges, if I could have found these edges would essentially form the clique. So that is essentially the k clique problem. Can you find these edges? All of these edges are touching both of these nodes. So in some sense, these are edges which have something to do with pairs of nodes. In the vertex cover problem, which I want to create, so some G tilde, every edge is sort of touching just one of those or maybe both. But soon as an edge is touched by a node, I have taken care of that edge. And I'm saying what can I do to this graph so that I keep the structure the same? I'm looking for that core structure in there. And my thinking is that since these are all about touching at least one, what I can do is I can go with taking graph G and producing the complement of this graph. If I produce the complement of this graph, all of these edges all go away. New edges are produced. Okay, so you suddenly have all of these new edges. So soon as all of these go away and new edges are produced, I suddenly realize that if I can use these nodes to cover it, I'm done. Okay, so if I take the complement, I lose those edges. I probably produce more edges. But I now realize that there is a hole here, and so I might be able to cover this new graph with other guys. That is the hint of the idea. If you cannot reach that idea, you are not going to be able to solve this problem. Okay, so what just happened is I gave you a polynomial time transformation. I am claiming that G tilde is going to be, by definition, complement of G, and I want K tilde to be n minus K. I now have to prove to you that this is the proper transformation. Mind you, you will have several tries of these transformations and you'll see that it's not working out. Or maybe within the single hit you will get it. Okay, but intuitively, essentially what I'm trying to do is I'm trying to maintain the structure. Okay, so to prove that an answer yes here is an answer yes here and an answer yes here is an answer yes here is the same thing as an answer yes here implies answer yes, answer no implies answer no. Usually it's very easy, just choose the easy path. You prove an answer this way, yes implies yes, and if you have to show no implies no is turning out to be difficult, prove yes equals to yes the other way. And one of those modus ponens or modus tonens is going to take care of things for you. So why is it that this is the case? If there is a K clique here, I claim that there is an n minus K vertex cover in G tilde. If there is a K clique here, immediately as I showed you, all these edges simply disappear. Right? And therefore, if I choose all the other nodes except these nodes, every edge is going to be incident on at least one of those. Because for an edge not to be incident on any one of those things, it has to be incident both sides out here. Is that making sense? If you choose all the other n minus K nodes as your vertex cover, then the reason you're going to get a vertex cover is because every edge I claim now is going to be incident on at least one of these nodes in G complement. The reason for that is that if it is not, then you have found an edge such that neither this side nor that side is incident on your vertex cover, the n minus K nodes. It essentially means that in this edge is essentially sitting among these guys. I've essentially set out the K clique and I'm looking at all the other nodes. But if this edge is in G tilde, then it means that it is not in G, but it cannot be the case because this is a K clique. Every element out there is connected. And therefore, if there is a K clique here, there has to be an n minus K vertex cover there, and we know which one the vertex cover is. Okay, so don't think in abstract. Try to connect the answers. That K clique is going to become the complement of the vertex cover on the right side. So if there is a K clique, there will be an n minus K vertex cover, and the other one is also very easy. If there is an n minus K vertex cover any place in that graph, that means that the remaining nodes, when you complement it back, will all be connected among each other, and the remaining nodes is K, and therefore you will find a K clique here. So, a k clique here implies an n minus k vertex cover there, and n minus k vertex cover implies a k clique here, and therefore, you have connected the answers. And this ends the proof for vertex cover being NP complete. The problem that you will get in the final exam, and I can guarantee you now you will get an NP complete problem, will be of difficulty of this nature. Okay? I will give you a problem and I will give you a very close problem and say assume that that one is NP complete. And you will have to show that this one is NP complete. And the way you will show it is that you will reduce that problem to this problem. Some of you will get it, some of you won't. Tell me if you have questions. Are you following what I am doing? Yes.
So let's assume there are no other nodes and only key nodes and they are all connected. So when it goes to vertex cover, it is still the same. Initially what I thought was let's assume that we remove all other edges. Just you have k.
See, you have immediately made a mistake. You are assuming that you know where those k are. This is one mistake that everybody makes. They say that I have seen the solution because, see, the way I describe things to you, you might be thinking that I know where the solution is. Mind you, that is not the case. I do not know where the solution is. If I knew the solution, this whole field would be gone. If I knew, given a graph, where the k clique is, we would not need the domain of NP completeness at all. We would have polynomial time solutions for it. We do not know. So, you cannot take out all the other edges. What I just did, you can see I closed my eyes and I did something which, regardless of where the clique is, I did the same thing. So, it is not dependent on where the clique is, if it at all exists. So, if you are looking for k to be n itself, that is actually easy to solve. You are asking whether the graph is all to all connected, which I can go and check. Okay. So, the k clique problem is a generic problem where you are given a graph and any number k. Some of those are easy, some of those are difficult. The easy ones we have polynomial time solutions to. In fact, if I ask you is there a one clique, you will always come and answer yes. If I ask you is there an n clique, where n is the size of the graph, you will have a polynomial time solution. You check and see whether all nodes are connected. It is these intermediate numbers where this problem actually becomes difficult. But that has nothing to do with NP completeness. In NP completeness, when I say let me assume that I know the clique, I am not saying that I really know the clique. This is all happening in my head. I am trying to build a transformation, and the transformation cannot depend upon the answer. Mind you, that is very important. After all the thought I did a transformation which has nothing to do with the answer at all. This polynomial time reduction that I did does not care where the clique is, if at all it exists. It simply goes and takes G complement. That is very important. If you knew where your clique is, and if your answer is that, okay, so here's my clique, I'm going to do this, immediately you get a 0. That's because you're assuming where the solution lies. That is where we started. We cannot seem to find where the solution lies. Speak up, because this probably is the last time I'll be able to tell you how to go about thinking about these things. It will take a little while for you to digest this. Okay? You try some of the ones that are sitting in the book, and maybe you will start getting a hang for it. If not, it's okay. Okay? Here's a big hole in your understanding of algorithms, NP hardness. Many people have that big hole. Yes? Okay. So, the transformation I finally suggested is simply the following. You give me the graph G and the number k in the k clique problem. This is the reduction I am trying. I need to produce a new graph and a new number. Sometimes this new graph will be the same graph. Sometimes it will be a different graph. This depends upon the problems themselves. But the new graph that I generate cannot assume either the existence of the answer, the certificate, or where it is. It has to be beyond that. So, the transformation I am suggesting is the following. Take graph G and take the complement of it, by which we simply mean for every pair of nodes, if you see an edge in G, do not put it in G complement, G tilde. If you do not see an edge there, put the edge there. That is simply the transformation. And what do I produce for the number k tilde? I simply say you take the number k, deduct it from the number n, which is the size of the graph, and produce a new k tilde. So, this, and this very clearly is a polynomial time reduction. I can do this in polynomial time, I can do this in polynomial time. I then take this and hand it to the vertex cover problem. From now on, it has nothing to do with solving the problem at all. Now on, you can get into the concept of NP completeness. What I am basically saying is that if you take this pair and give it to the vertex cover problem, if that person says yes, for whatever reason, if that person says yes, I have a vertex cover of size n minus k, I know that that corresponds to a k clique someplace. And if that person says no, there is no vertex cover of size n minus k, then I know that there is no k clique there. And the way I think about it is, I play both games. I say assume that there is a k clique here, then I can show you exactly where the vertex cover is here. And assume that there is a vertex cover here, I can show you exactly where the k clique is here. But I am not going to assume that it exists or does not exist, because that is beyond this game. Essentially, I have just connected answers. If there is an answer here, I will tell you where the answer is. And because of that, I claim that I have a correct polynomial time reduction. I am not going to assume that the answer exists, but if it does, then I can show you where the answer exists in the other place. Okay? Yes, more questions. It is probably good for you to listen to this lecture a couple of times for this thing to slowly seep into your head. Okay, because you will be asked one of these things, and there are so many pitfalls. It's more difficult to even start solving the problem when you are not understanding what you need to do. And in order to understand what is expected of you, what you should be doing, you need to understand this properly. That the way to solve these problems is to assume that there is an answer there and make a transformation which does not depend upon the existence or where the answer is, such that that answer there shows up in some answer here. And likewise. And don't go about producing a transformation that requires the answer. If you say, I am going to take the k clique and remove all the other edges, that one, assume that it has a k clique. It's a problem which asks whether there is a k clique or not. So, there might not be a k clique. And two, it assumes that you have solved the problem. If you can find the k clique, come talk to me. We do not know how to solve these problems. So, don't try to solve this problem. If you want to try to solve this problem, do it 2 semesters from now, when you start realizing that you are a genius and maybe you will be the one cracking it. We do not know how to solve these problems in polynomial time. Mind you, when I say we do not know how to solve these problems, what I mean is we do not know how to solve these problems in polynomial time. Given exponential time, we can solve these problems. Why? Because the definition of NP tells you exactly that. If you can run through all certificates, you have a polynomial. So, if you can run every certificate possible, you can verify in polynomial time. It's just that you have exponentially many certificates out there. That is why we bring in this notion of an oracle. Right? If I were the oracle, which I am not, I would essentially give you something that might or might not be the certificate. So, your way of actually doing it without the oracle's existence is to actually take certificate after certificate after certificate. These are not really certificates, these are just strings of that length. Check them all. But checking them all is brute force, gives you an exponential time algorithm. Is that making sense? That leads me to Cook's theorem. The genius of Cook is to realize that that kind of solution to the problem is exactly why these things are so difficult. Okay? So, let me step back and give you the high level description of Cook's theorem. That the Boolean circuit satisfiability is NP complete. Okay? By which, what Cook is saying, you take any problem in NP and I can prove the following to you. By which I mean that you give me a problem of your choice, and I will show you a polynomial time reduction to the Boolean circuit satisfiability problem. Any problem. Okay, on the surface, it looks like there is no way Cook can go about showing this. These are all problems which I'm not even aware of problems that are in NP. How am I supposed to show this? Well, Cook's genius is to realize that if a problem L is in NP, if you know of a problem that is in NP, that you have come to Cook to say, hey, show me this one, Cook immediately can assume the following. Because you know it is in NP, you know that it is polynomial time verifiable. Okay, so L essentially comes with a polynomial time verification algorithm. Are you following me? Any problem that is in NP, by definition, has a polynomial time verification algorithm. What Cook is going to do is do the following. You take your algorithm, and in the end, you have to run the verification algorithm in a computer. And any computer is a bunch of gates and a bunch of flip-flops, registers. I can open up time. So I can essentially take your computer, whatever your verification algorithm turns out to be, I can use the way the computer actually goes about solving it and make a combinatorial circuit out of it. That is essentially what Cook suddenly realized. That any problem in NP clearly has a verification algorithm, and that verification algorithm runs in your computer via a loop. So essentially, I'll show you these pictures, right? You take stuff out of memory and put your stuff back into memory. But since it is going to take only polynomial time to run through there, he is going to open that up into a sequence of layers. And he's going to say that you run through these layers, this is going to be your solution. And that is a massive combinatorial circuit, massive, but still polynomial in the size of the problem. He's going to now use that and set it up as your Boolean circuit satisfiability problem. That's the basic idea. So how does it do it? Well, assume that L is in NP. Then I'm going to assume that there is a verification algorithm, an algorithm that takes in two inputs, right? This is the description of the problem itself, and this is the certificate. Not to be too abstract, let me be a little more concrete. Let's say that this L is a K-clique problem. Then A is the verification of the K-clique, by which I mean that it is the one that sorts out all the edges. How do you solve the K-clique problem? How do you verify the K-clique problem? Not solve the K-clique problem. How do you verify the K-clique problem? What is the certificate? The part of the clique. And then you go and essentially for every pair of nodes, you go and check whether the edge is there. Right? So this is an algorithm. You can essentially say, take your certificate, that is going to be your certificate, Y. Take your graph, this is going to be your graph. You remember, this is a general algorithm that runs on some graph with some certificate. That's what I'm trying to show you. So this algorithm is essentially going to take that certificate, which is going to be a bunch of nodes, and then for every pair, so you'll put two for loops there, for every pair of nodes in Y, check and see whether the edge exists in X. For any given problem in NP, you will have this general algorithm A, and you will have X and Y. Two open spots where you can put your problem description and your certificate, and it's going to verify it for you. That is the definition of being in NP. I'm going to take the machine code of it. So I'm going to compile this algorithm and look exactly what it looks like. So this, let's say, is my memory. So what I'm looking at is a very primitive computer, not the ones that you use nowadays with caches here and caches there. I'm looking at the most primitive of computers. It just has a memory and it has a CPU, and the memory interacts with the CPU all the time, and the CPU goes and does something. Okay, so usually what happens is that you have a program counter. This is, if you take a course in architecture, you will know the first few lectures they describe exactly how this thing goes about. There is a program counter. This is where your A is going to sit. Okay? And this will be where your X sits. You will have some space for Y, and you will probably have some working memory. And essentially what you have is a massive combinatorial circuitry, that is your machine M, that essentially takes stuff from here, okay, and based on the nature of whatever is here, that so essentially it runs the thing through this combinatorial circuit and goes and fixes something in this. Usually what it does is it changes the program counter by incrementing it. It changes something in X, it changes something in Y, I don't know. It essentially takes that in the next clock step something changes in this memory. In the next clock step again something changes in your memory, and so on and so forth. And those changes are happening because of a machine that takes in all of this stuff and is a big combinatorial circuit here of constant size. What Cook envisions is that he says, instead of putting it back there, why don't you do the following? Step it up one, something else changes here, something changes there, something changes there, I don't care. And Cook says that if you unravel this, so clock step 1, clock step 2, clock step 3, and so on and so forth, because your verification algorithm is only polynomial in time, in the size of this, I will therefore have only polynomial layers. Okay, and then I'll take these things out and just, so these are just holding places, I'll just connect those wires. So these wires will just directly get connected to the other side. Remember, that is going to go to the machine on the right side. So rather than sit them in memory and then again send them to the machine, I will just connect these wires because these are directly connected. So essentially I'll have M with a bunch of wires going out to another version of M, with a bunch of wires going out to another version of M, and so on and so forth. And that is going to be a massive combinatorial circuit. Now I do the following. This is the part that I just talked to you about. I'm going to leave these guys exactly as they were. So the program counter will probably be 0, 0. You'll have some machine code here. So this is essentially the machine code for your algorithm. I will take X, have it be whatever be the problem. So here too, I will take Y, which is essentially the certificate, and open it up. And I know that on the other side, when the answer comes out, when the verification algorithm has verified that particular circuit, there will be some spot there where it goes and says 1 or 0, right? If the verification turns out to be yes, it says 1. If it doesn't verify, it says 0. So that spot I'm going to take out. And I'm going to claim that this massive circuit that I have is my Boolean circuit satisfiability problem. The claim is, given this circuit, if this is satisfiable, then your problem has the answer yes. If this is not satisfiable, your problem has the answer no. Why is that? If this is satisfiable, it means that there exists some assignment of zeros and ones here that is going to produce a 1 on that side. that is your certificate. It basically points to the existence of a certificate. And if this is not satisfiable, it essentially means that this circuit, regardless of what you do on this side, is going to give you a 0 on that side. That essentially means that there is no certificate. And the crux of Cook's theorem is essentially this. Now, of course, Cook's theorem goes on into the details of just making sure that this massive picture that I drew for you is a polynomial sized thing. He also has to show that this transformation that he does, this taking the problem and turning it into this circuit, that itself is polynomial in size. So, there are a lot of details to be taken care. They are not particularly important. Well, they are important in terms of the result being true. But the insight is this. Cook certainly realized that any problem which has a verification algorithm runs on a computer and verifies. And something running on a computer has to do with ones and zeros running around. And he can just open it up into a combinatorial circuit. Did that make sense? This was the first problem that we found was NP hard. And soon after, many problems came, which Karp and many other people started showing are NP hard, until we suddenly realized that all the problems that we haven't shown polynomial times for, they are turning out to be NP hard. Right? For the longest time, we would look at all kinds of problems. Some we would have polynomial time solutions, others we would not. And we let it be. And then suddenly some people start showing, hey, that one that you could not solve, that's NP hard, that's NP hard, that's NP hard. And we sort of took care of almost all of them. Graph isomorphism we do not know is NP complete. Graph isomorphism sticks out as one of those crazy problems for which neither do we have a polynomial time solution, nor do we have a proof that it is NP complete. We strongly suspect that it is not NP complete, that it has a polynomial time solution maybe, but we haven't found one. Yes?
If the not equal NV, then there will be a subset that is not neither in V nor in NP complete.
Okay, yeah. So, there is a possibility then that, yeah, the graph isomorphism problem is neither in P nor NP complete. So, that is a claim. We have solutions for the graph isomorphism problem that is exponential, but not fully exponential. It is not the brute force kinds of exponential. So, we have been managed to shave off a little, but we haven't shaved it off enough to bring it into P. This is the reason why I said that if there is one problem that will stick with you for a while, which it is going to be the graph isomorphism problem. There are many other problems that we have shown to be NP complete. Let me list you a couple of those so that you know what these are. So, we have already done the Boolean circuit satisfiability. We have the 3 CNF SAT. I claim that it is trivial to then show that CNF SAT is NP complete. Why is that? If I ask you in the exam, prove that CNF SAT, where the constraint of 3 is not there, why is it that this is trivial? It is the same thing. There is no transformation necessary at all. A 3 CNF SAT is certainly a SAT. A CNF SAT. Right? A CNF SAT is not always a 3 CNF SAT, but a 3 CNF SAT is a CNF SAT. So, this need not be proved. So, we have K clique. I showed you the vertex cover. There is the K independent set. The K independent set problem is the flip of the K clique problem. It asks whether there are K nodes out there that are none to none connected. The K clique problem is all to all connected. The independent set problem is, can you find me K nodes out there such that none of these guys are connected? how would you do the transformation here? How would you go about showing that K independent set is NP hard? We know that you can do the ease in NP part. You will reduce K clique to the independent set problem. You are trying to prove that this is NP hard. So, you will choose an NP hard problem and you will try to do the reduction. So, you will do K clique in polynomial time independent set. You will be given a graph G and a number K here. You want to produce a graph G tilde, a number K tilde here. What would your transformation be? Okay. So, immediately you can see independent means nobody, K clique means everybody. You immediately know that G tilde is actually G complement. What is your number K tilde going to be? K itself. So, you can see that the independent set polynomial time reduction is very close to the vertex cover problem's polynomial time reduction, except that in the vertex cover problem we took n minus k. If you did not get this transformation, think about it for a moment before coming and talking to me, because this would be a good exercise to work out in your head. Why it is that I took the complement of the graph and K tilde to be K itself. Okay, so, you have these. You have many more. So, for example, you have the Hamiltonian circuit problem. What is the Hamiltonian circuit? A Hamiltonian circuit, in the simplest case, given an undirected graph G, the question is, can you find a cycle that is simple that goes through all the nodes? What do I mean? I mean, can you give me a path in this graph that starts with a particular node, runs through all the nodes, is allowed to go through every node exactly once, not more than once, but is not allowed to miss any node. So, essentially you have to find a bunch of edges such that you can go and hit every node exactly once without going back to that node and then coming back to this final node. That is called the Hamiltonian circuit. So, some graphs have Hamiltonian circuits. This has a Hamiltonian circuit, essentially the simple that. Some graphs do not have Hamiltonian circuits. I can produce a very simple graph for you which does not have a Hamiltonian circuit. In this graph, if I started from here, I cannot come back to this, right. So, it is very easy to produce graphs which have Hamiltonian circuits and graphs that do not. The question here is, given a graph G, is there a Hamiltonian circuit? It turns out to be a terribly difficult problem, because we have shown that this is NP complete. You then have Hamiltonian path. The only difference between Hamiltonian circuit and Hamiltonian path is that you do not have to return to the original node. So, you start someplace, you go through all the nodes in the graph, you are not allowed to go through any node twice, and you stop someplace else. That is called the Hamiltonian path problem. This also has been proved to be NP complete. You then have the subset sum problem. The subset sum problem is a peculiar problem in a different domain. You are given a bunch of numbers and you are given a new number, and you are asked whether there are a bunch of numbers here that I can add up to produce this number. You are given a set 5, 17, 22, 11, 52, and you are given a number 19. Your question is, can I take a bunch of these numbers and when I add them up, I will produce the 19. Sometimes you can, sometimes you cannot. That is called the subset sum problem. This too has been shown to be NP complete. There is an equivalent problem where you are given a set of numbers and you are asked, can you partition this set into two pieces such that the numbers here add up to be the numbers here. It is called the set partition problem. That too has been shown to be NP complete. Given a set of numbers, can you just pick out a bunch of numbers so that when you add these guys and you add the other guys, they will come out to be the same. It is called the set partition problem. That is NP complete. The three colorability problem is NP complete. Given a graph G, can you color the nodes using 3 colors so that no 2 nodes get the same color if there is an edge between them. This is used in painting maps. That is NP complete. Minimum spanning tree is not. Okay, so we spent the entire semester looking at problems for which we have answers. There is this whole domain of problems that we do not have answers to. They are all turning out to be NP complete, and because they are all NP complete, you can choose the one that you love the most, for which you have the best feel, and try to crack it. If you can show any one of these has a polynomial time solution, every one of these have polynomial time solution. In fact, all problems in NP have polynomial time solution. Yes? What? One of these might be in the exam. Of course, you will not get a problem in the exam where it takes you a lot of time to understand what the problem is. I will give you a problem which might be in this set, might not, but it will be something that as soon as you read the problem, you will know pretty much what the problem itself is. Let us take a break here, we will come back and we will do the last lecture.